Hi, everyone. Thank you for attending. We will get started in just a few minutes here. Can you see my screen? All right, we'll get started as people trickle in. So good morning slash afternoon, everyone, and welcome to today's webinar hosted by the CHA and GHD. In this webinar, we will review GHD's H2 Now report and highlight practical examples from ECHO, TC Energy, PG&E, and Dominion Energy, who are trailblazing hydrogen blending projects. My name is Tony Saha, Marketing Communications Manager at the Canadian Hydrogen Association, and I'm speaking to you today from Edmonton, Alberta, which is the traditional ancestral unceded territory of many First Nations, such as the Cree, Dene, Anishinaabe, and Blackfoot. Oh. For those of you who are not familiar with the CHA, we are a national industry association established in 2009 with a history that spans over 50 years. With regional affiliates in BC, Alberta, and Ontario, we support our members with advocacy, communications, networking, and government relations. Currently, the CHA is recruiting co-exhibitors for the Canada Pavilion at H2 Meet in Seoul, Korea this September, and at the Hydrogen Technology Expo in Hamburg, Germany this October. Attending with the CHA will make your organization eligible for partial travel reimbursement, B2B matchmaking support, and networking opportunities. If you are interested in this, please reply to the email I will be sending to all registrants after this webinar. Sorry, it seems I'm having some trouble going through my screens right now. All right, I'm just gonna leave the screen alone and just go through the rest of it. Just some housekeeping rules before I introduce our speakers for today. Please note that this webinar will be recorded and held in accordance with the CHA's competition law compliance policy. Please feel free to enter any questions that you may have in the chat section. We'll be sure to get to your questions during the Q&A segment following the presentation, where you will be able to turn on your mics and cameras and ask the questions yourself. All right, this works. So now onto the main part of the show. I'm pleased to introduce our guest speakers for today, Fred Taylor from GHD. He has 40 years of work history on a wide variety of engineering and construction projects throughout North America. Fred was a founding member of GHD's Global Future Energy Initiative and leads GHD's North America hydrogen team, working to help clients transition into the energy space. Seems Cole, I can't get your slide up. But Cole Zosky is a senior engineer on ATCO's and hydrogen projects team and is focused on ATCO's transition to hydrogen. He is involved in associated organizational change management programs and the construction of ATCO's blended and pure hydrogen projects. Next, I can get Caitlin's screen up now. Caitlin Connolly is a project engineer with the Canada Gas Business Unit of TC Energy. She is currently working on hydrogen initiatives and feasibility assessments that consider integration with existing Canada Gas assets. Let's see if I can get the next speaker slide up. Nope. Right before this, there was a slide for Kevin Pease. He's a senior gas engineer at PG&E on the greenhouse gas emission strategies team, focused on decarbonizing the gas system through the use of hydrogen with a focus on preparing the gas system for transporting hydrogen natural gas blends. And last but not least, Brendan Shaw is a chemical process engineer currently with GHD and speaking on behalf of Dominion Energy today with 8 years of experience in the design of industrial facilities in various sectors. Now, enough from me. I'm passing it off to our first speaker of the day, Fred Taylor.
Thank you very much, Turney. GHD is very happy to co-host this event. Just going to try and pull up my slides here. I seem to be having the same trouble you're having, Turney. Everybody see my slides okay?
Are you on the first slide, Fred?
Yeah.
It's showing. Oh, now it's showing the first slide.
Boy, it's tricky today. Okay, thanks, Turney. As I said before, GHD is very happy to co-host this event with some of our clients who are doing great things in the blending space. So I'm going to try and frame the conversation around a thought leadership piece that we issued earlier this year, and then talk a little bit about some of the challenges and opportunities around hydrogen blending to introduce the topic for our client projects. So this is what I'm going to go through. Like I said, the campaign opportunities challenge, a little bit of the conversion process, and I'm going to leave you some takeaways around hydrogen blending. So the thought leadership piece we did called H2 Now was earlier this year. We focused on 3 areas: hydrogen market readiness, community and stakeholder readiness, and pipeline infrastructure readiness. And I'll go through each one briefly. So hydrogen market readiness, we looked at all the different signals in the market that we're seeing. So there's many different things that are showing that the market is ready and it's growing and it's starting to adopt hydrogen blending globally across North America and Canada as well. So many things like technology advancements, adoption in different industries that are hard to abate, significant amounts of funding in different areas, and decarbonization incentives, research and development things. We're seeing decreasing hydrogen production costs, development of end user markets, and a lot of worker training programs. So in summary, even though only 10% of the 600 large-scale hydrogen projects worldwide have reached final investment decision, a lot of projects are still going on, just a little bit slower and a little bit smaller scale, but there's a significant market getting ready to transform hydrogen blending across the globe. Also along the market lines, I wanted to share this story map that we prepared for a client 3 years ago, and we're keeping it up to date. So this tracks over 100 global blending projects, demonstration research projects that are going on worldwide. It's an interactive GIS tool where you can actually interact with each project and get all the information around individual projects across the world, what they're doing, where they're at, where they're going. There's a huge amount of information here, and we're keeping this up to date for multiple clients as we go, and it really helps us provide a good up-to-date view of what's happening in the market worldwide. And there's significant activities going on. Next up was community and stakeholder readiness. So The community stakeholders are so important when you're doing a hydrogen blending project. And the other category of stakeholders that is really important is the internal stakeholders. The utility, the energy company that's doing the project is just as important to have them on board as well. So when you first look at stakeholders, you need to map all the potential stakeholders that are going to be impacted or affected or want to be involved in your project. You really need to engage them with good dialogue, introduction, and awareness around hydrogen, and then get a lot of feedback. So you're really managing those connections and helping them bring them to your project to help you with your project. So a lot of people, internal, external, they say, why are you doing this? Who's going to pay for it? Is it going to be safe? Who else is doing it? The typical kinds of questions you get, and you need to be ready with a whole bunch of answers around that. And this engagement process is so important for hydrogen blending projects. And finally, pipeline infrastructure readiness, and I'll drill into this in a little bit more detail. One aspect in the graph on the bottom left-hand side, you can see that it isn't a one-to-one relationship. So for every volume of hydrogen you blend, you don't get 1%, one volume of carbon dioxide reduction. You actually get a sliding scale. So you really need to get to 100% before you get 100% decarbonation. And that's an important message. It's not straightforward how to figure out how much decarbonation you're going to get. And I'll go through these in the next slides. So what are the opportunities around hydrogen blending? This is a map showing the natural gas networks, most of them in the United States, and Canada is very similar. And if you think about that network that we built over many decades, there's over 3 million miles of pipeline. 90% of it is lower pressure distribution, 10% higher pressure transmission. And it's so vast, one new customer is added to this network every minute in North America. We've spent trillions of dollars on this infrastructure. We spend tens of billions of dollars on it every year, maintaining it and operating it. There's hundreds of gas utilities that manage this network. It's very highly regulated, and of paramount concern is the reliability and the safety are absolutely critical for this network. And if you can think about the numbers of natural gas in the US, it's about 32 trillion cubic feet per year. That's a huge amount of gas. That's half of the volume of Lake Ontario, just a massive amount of gas. And it's used across everything, all sectors, business, industry, power plants, homes. So very widespread use. This is a very large infrastructure that we built. So why are we looking at repurposing and blending? One of the fundamental reasons is if you use existing infrastructure, it's only 10 to 20% of the existing cost versus building a new pipeline, which is very difficult to do, as we're seeing out in society. It's much faster, there's a lot less environmental impact, and much more positive community engagement. And because you have all these thousands of users on the pipe network already, there's a lot of opportunities to help them decarbonize. And it really is a pathway to long-term transition. There's many examples of pipelines that have been converted to blends or 100% hydrogen. One along Beach, a crude oil pipeline, actually, that's now 100% hydrogen through a residential area. Backbone pipelines in the Netherlands and Germany. And there's a lot of activity in Australia where we're doing much work around converting pipelines. So what are some of the challenges? So hydrogen is just different than natural gas. It's more flammable, it's more potentially explosive, it's got a different heating value. So that provides really significant challenges around blending it into natural gas and then using it at 100%. So integrity is always something people hear about when there's metal steel pipelines. The hydrogen molecule is so small, it gets right into the structure and it can cause embrittlement and cracking and that type of thing. So there's a real integrity issue that needs to be addressed. Safety, obviously, because it's a different kind of gas. Metering gas quality is different with blends than it is with natural gas. And then compression is very different for hydrogen. You need a lot more energy to compress hydrogen than natural gas. And you need to manage the network, including things like large underground storage caverns that are part of lots of networks. And then end users, there's thousands of different end users. They all have different equipment, different appliances, different applications. You need to look at some of that equipment because a lot of it can accept a blend, some can, and some the OEMs are working to make it so it can accept hydrogen. So broadly speaking, gas transmission versus distribution. Gas transmission, these are the large interprovincial, interstate, intercountry diameter steel pipelines that provide a lot of gas long distances, they're a higher risk because of the higher pressures and the steel piping. So that diffusion and brittlement issue becomes a thing much more enhanced with potentially with gas transmission lines, and it needs to be addressed. And if you think of our networks that we built over many decades, the steel types have changed, the different ages of networks in different places, the workmanship has changed around welding and installation. There's a lot different when you introduce hydrogen, the velocity changes, the compression changes, all these different things need to be considered when you're looking at blending into a gas transmission line. On the other hand, gas distribution lines, a lot of them are plastic. They're newer, they're a lot less to be impacted by embrittlement with hydrogen, so there's a lower risk. And they also operate at lower pressures, which makes it a little bit easier. So similar kinds of issues need to be addressed, though, with all the equipment around the valves, the heaters, the meters, all the things that go with the network. Because if you blend hydrogen, the hydraulics change and the safety potentially changes as well. And you need a different instrumentation to be able to monitor and measure the blends properly. So the conversion process, just very generally, there's a very structured process of engineering assessment that you really need to go through. So the first step is to look at in very good detail around the particular part of the network that you're trying to look at converting to a blend or 100% hydrogen. All the information on the materials, the construction, how it's operated, how it's inspected and maintained. You really need to evaluate that versus the large body of information that's been developed globally in terms of what you can and can't do with blending and pipeline systems. Based on that, you have a good general sense of what you can do or not do in terms of blending. And then a lot of times what you'll do is some actual laboratory testing in the hydrogen environment to verify some of your desktop assessment work that you've done. And then based on that, you'll look at all the other aspects of operating the pipeline and come up with a conversion plan, including where the hydrogen comes from, how much you're going to blend, how you're going to scale it up, how to deal with the end users and the community and the regulators, et cetera, et cetera. And then you have an implementation plan. So a very broad brush, that's the process that you follow, and it's been followed on many projects globally, and it's being followed on projects in North America as well. This process takes up to 3 to 5 years to do, depending on the size and scale of project you're doing, how much of a network you're trying to convert, whether there's sensitive users or end users and that type of stuff, the regulatory environment, et cetera, et cetera. And finally, just some takeaways. So really, I want to just say that this widespread existing natural gas network that we have is very amenable to hydrogen blending. And we should be using that network as part of our energy transition. It's already built. It's a lot easier to use infrastructure we have than to try and build new infrastructure and spend more money, have more environmental impacts and more concerns about building new infrastructure. Because of all the uses of natural gas, the thousands that are in place already, there's very good opportunities to decarbonize, especially in hard to decarbonize industries that don't have other technologies readily available, like cement plants and steel plants and power plants. But that being said, there's absolutely technical challenges, like I talked about, economic challenges until the hydrogen economy gets to scale, regulatory challenges. It takes time to change codes and standards and regulations. You want to be safe and reliable when you change networks to hydrogen blending. And the process that you follow, you really want to deal with these challenges head on and be comfortable and conservative that you have a good plan for addressing all the issues and manage them going forward when you do a project. So with that, I'm going to hand it over to TC Energy and ATCO, two of our great clients, to talk about their project. Thank you.
Caitlin, feel free to share your screen.
And everyone just hold on. Okay. So I hope my slide is showing.
Yep.
Perfect. Thank you. So my name is Caitlin Connolly. I am a project engineer with TC Energy, and joining me for this presentation is Cole Zotchke. He's with ACO and the hydrogen team over there. We are going to be presenting on our work with GHD that we've been doing, the feasibility for changing of service fluid from natural gas in an existing transmission pipeline to pure hydrogen or a hydrogen blend. I want to take a moment and just showcase our companies we've been working with on the side here. So we've been working with GHD. They've been our engineering consultant for the project. We've also been working with Delphi. They've been helping out with the environmental benefits, quantifications. CFR Technologies has been doing our material testing. And we do want to give a big shout out to Alberta Innovates. They've actually funded 50% of this project. So with that, I'm going to hand it over to Cole. If I can change the slide. There you go.
Thanks, Caitlin. Just to chat about the project goals. So we're looking to advance for TransCanada ACO and ultimately the industry knowledge of hydrogen high pressure transmissions. So we're trying to identify the knowledge gaps and advance our practical knowledge and actually how to utilize our existing assets for our high pressure hydrogen transmissions. The goals are also to understand costs and benefits for blending hydrogen into our assets and equipment, as well as looking into supporting the regulatory framework that ultimately governs the hydrogen blending and conversion opportunities we have, as well as assessing the feasibility of converting a large diameter, high pressure transmission natural gas pipeline to pure hydrogen service or a hydrogen blend service. And the scope of work here is a Alberta transmission pipeline was ultimately selected as the study location for assessing this hydrogen conversion. This pipeline consists of 131 kilometers of 20-inch line operating at a MOP of 9930 kPa. It was constructed recently back in 2019, and it actually connects a producer to two natural gas fired power plants. The pipeline consists of 120 kilometers of main line, a meter station, 11 kilometers of lateral pipeline, 3 valve sites, and 2 riser sites.
Perfect. Thanks, Cole. So for this project, we've been using CSA Z662 Clause 17 as our basis. Back in the 2023 revision, Clause 17 was introduced, and what it says is it requires an engineering assessment to confirm the max allowable hydrogen content and the maximum operating pressure of the system when we introduce hydrogen in there. So this is kind of like what we've been basing the whole project off of. All the criteria for that engineering assessment can be found in Clause 17 and is kind of what we've been figuring out how to address through the project. Also, I do recognize there's a lot of words on this screen. So these slides will be shared after the webinar if you want to read a little bit more, and feel free to reach out afterwards. Our methodology for the project was kind of just building off of what Fred was talking about earlier. We're stopping at the feasibility assessment though, and this is very much about asset readiness versus operational readiness. So a lot of our operational procedures, they're being looked into through other initiatives. So for this project, we're doing phase 1 and phase 2 for the asset readiness. Phase 1 was all about scoping and setting boundaries, understanding what we don't know. Kind of the last deliverable from phase 1 was a very comprehensive design basis memorandum. And that feeds into phase 2, which we're currently in on the project. Very much getting into the details, doing the material testing. We'll be doing a process hazard analysis workshop. And having the engineering assessment as the final deliverable of this phase. This slide is all about, from a screening assessment, we identified that this pipeline system is likely suitable for introducing hydrogen. MOP restrictions may be required. Overall, if you look at its bullet point 4 here, the overall outcome was an amber assessment on a traffic light system. So it wasn't a clear go ahead, just start introducing hydrogen. And it also wasn't any fatal flaws. So this amber pretty much told us that we would have to do some further material testing, some more desktop analysis before we can give more of a definitive answer. And then if I just go to the next slide, The operating envelope and capacity were also assessed because introducing hydrogen as a different fluid than natural gas, it had hydraulic implications, sorry. And so when we talk about operating envelope, it's really talking about the operating limits at a hydrogen volume that a pipeline can operate at with meeting acceptable safety and risk criteria. So it was parameters such as looking at pressure, temperature, hydrogen volume and concentrations, velocities, etc. So we did run it through the screening assessment, and we did do a preliminary capacity assessment from there through our system design team. For equation of state, they used the Redlich-Kwong equation of state for this initial assessment. Um, you'll see it is 0.3 there. It talks about a energy basis reduction of about 15% if we're putting through pure hydrogen. And that was verified through this assessment. But for this phase two, we'll be kind of going into that a bit more. We'll be refining the MOP calculations that were done because we use quite conservative calculations for phase one. And then those feed right into the capacity assessment. So that will be refined as well going in. Bullet point 4 talks about change in gas velocity. So that's something that will be looked at a bit more in phase two as well. And yeah, we did do some low percentage blending implications on the hydraulics, and it really wasn't that much. But the MOP, yeah, definitely was reduced with 100% hydrogen. So we'll be looking at that one a bit more. And then on to Cole again.
And then, yeah, a big part of this project was the material testing in the hydrogen environment to identify the long-term impacts that hydrogen exposure has on the pipe. So instead of focusing on the immediate hydrogen exposure, which is better understood in the industry, this project actually focused on the long-term hydrogen exposure testing. So testing is being completed in 100% hydrogen environments as well as in air environments to compare the differences in how hydrogen actually impacts the pipe. The key tests include tensile testing, fracture toughness, and the fatigue testing. And then we're actually utilizing material left over from the pipe for this material testing. And the project, we're just using one specimen of wall thickness. Again, this is a feasibility assessment and isn't going to be obviously proceeding with injecting hydrogen very soon. However, it's identified that obviously with trying to move forward, we'll have to do further testing and wall thickness and the different wall thickness of the pipe there. So, and this is what CFER is taking care of for us.
That is our slide deck, everyone. So I'm going to stop sharing my screen. But I believe there might be question and answer period later. So if you have questions, please let us know.
Thanks, Caitlin.
Thank you, Caitlin and Cole. Our next speaker is Kevin from PG&E.
Okay, can you hear me and see my slides?
Yes.
Great. Good morning. Thank you for the opportunity to be here. It's great to hear from Cole, Caitlin, and Fred. Similar work here down in California. My name is Kevin Pease. I'm an engineer in Pacific Gas and Electric's Greenhouse Gas Emission Strategies team. I'm going to share a bit about a project that we call Hydrogen to Infinity. There we go. So first, a bit about Pacific Gas and Electric. The gas side of our business is in Northern California, consists of over 10,000 kilometers of transmission pipe stretching from the Oregon border to Topak in the south, the border with Arizona. This large system, PG&E system, and also throughout California, presents a large opportunity for decarbonization with hydrogen blending. A 20% blend of hydrogen could amount to a decrease of about 7 million metric tons of CO2 emissions reduction. And at 4 metric tons per vehicle per year per the EPA, that would be the same impact as removing about 1.5 million gas-powered vehicles from the roads. So I'll now start a little presentation about our project, Hydrogen to Infinity. This was a little graphic of what this might look like in the city of Lodi through work that we did with GHD. So PG&E is working to operationalize our Hydrogen to Infinity facility by 2027. The project's a large-scale, long-term demonstration of hydrogen blending in a natural gas high-pressure transmission system. It'll consist of a 1 to 2 mile transmission test loop with new and vintage assets representative of those found in the natural gas transmission system. Hydrogen blend levels are planned at 5%, followed by stepwise increase to 10, 15, and 20%, and potentially beyond that in the future. Operating pressure will be 720 psi, or about 5 megapascal for those metrically minded folks. This, which I like to be as well, I'll say, but this aligns with the ANSI 300 standard, and we intend to operate the facility for at least 10 years. This is another depiction of what this facility could look like. On the left is the existing power plant owned by Northern California Power Agency. They have a turbine already installed capable of 45% hydrogen blends. They plan to do electrolytic hydrogen production, which some of that would be used in our test loop. The preliminary test loop design will have multiple areas for long-term testing of pipeline materials, transmission equipment, and hydraulic performance testing. There are 8 proposed test areas shown on the slide. I think that I apologize. Let's see, 8 proposed test areas are shown on the slide, which include inline inspection tool trials, welded high-strength fittings, repair sleeves, live welding and repair testing area, pipe and pipe coating testing, transmission equipment, long-term trials, compression testing, blending and odorant injection trials, as well as a leak detection testing area. This one is the aerial view of the project. Apologies for that. Our project partners to date on the left, who helped us with our feasibility study, with GHD being our main collaborator in this project. The city of Lodi has been very supportive. I recommend for any project that you're looking to do, start with stakeholder engagement early and often. We're very fortunate that the city of Lodi owns this land, and they're very supportive of our project. So just one note about stakeholder engagement. This is a project timeline. We completed the conceptual engineering design and a large portion of the pre-FEED study back in 2022. In collaboration with the other California joint utilities, we've submitted a mandated hydrogen blending demonstration application to the California Public Utilities Commission in March of this year. In parallel, we're working to launch our joint industry project to run over a 1 to 2 year period that would move the engineering design of the project forward. Following completion of the engineering design, we'll move to procurement, construction, and startup hopefully by 2027. Now I'm going to take a few minutes to talk about the joint industry project for this project. We're inviting interested parties, whether you're a gas utility, Cole, Caitlin, technology provider, or OEM, to join us in the joint industry project. The intent is for the facility to be representative of most legacy steel infrastructure in North America and function as a test bed for the industry. Electric Power Research Institute, also known as EPRI, will administer the JIP and provide strategic technical support for the design of the test loop and test plan vision. The joint industry project will include the FEED and detailed engineering studies for Hydrogen to Infinity's transmission test loop. These are pre-operational stages of the demonstration are critical to ensure the comprehensive design of the facility is completed, and we don't want to miss anything before it comes operational. Once the facility goes live, this will evolve into a new JIP to oversee long-term full-scale testing. The three main objectives are understanding the long-term effects of blending in natural gas in a test facility that represents much of the existing natural gas transmission pipeline infrastructure of the JIP funders. Second is to identify the conditions or mitigation measures, if any, that would ensure a 20% hydrogen blend will not pose added risk to the common carrier pipeline system. And third is to increase understanding of the operational limits of existing natural gas transmission pipeline infrastructure when injecting hydrogen blends at 20% or possibly beyond. So on the left side of this slide, it would be great to have your participation in the JIP. Your natural gas infrastructure would be representative in the demonstration's full-scale testing through the engineering design contribution of your pipe and pipeline components. These need to be set aside before the demonstration goes live and accounted for in the engineering design of the test loop and installed during the construction phase. Your guidance to ensure all the right full-scale tests are designed for. We don't want to find out we've missed a critical test after it's been operational. If you're interested in building a similar facility in your area, you'll have access to the blueprints to do so. And so you'll have name recognition as a leader in this big final step to really move hydrogen blending forward in North America. On the right side of the slide are the responsibilities of members for the Joint Industry Project. These include active engagement through feedback on the test loop plans and design, research objectives. We're using the design from the FEL1 study, as well as hydrogen blending requirements from the California Public Utilities Commission decision ordering this blending demonstration. Documenting and setting aside your vintage assets and technologies for inclusion in the test loop. And finally, a contribution, financial contribution to support the engineering design. We're looking for $160,000 per member over a 1 to 2 year period. And finally, here were anticipated tasks and deliverables for the project: identification of key decision points in the test loop design, a test plan vision that will accompany comprehensive engineering design of the test loop, inventory of vintage assets for inclusion in the test loop, and solicitation for phase 2 of the JIP, pending external funding for procurement and construction of the project. And EPRI, a little bit more about EPRI, the third-party administrator. If you're not familiar with them, they lead the Low Carbon Resource Initiative along with GTI Energy. It looks at fundamental advances in a variety of low carbon electric generation technologies and low carbon chemical energy carriers, such as clean hydrogen, bioenergy, and renewable natural gas. EPRI will provide strategic technical support for the design of the test loop and test plan vision. And finally, last slide, it's a summary of the JIP and the full value of phases 1 and 2, importance of being an early stage partner with us in phase 1. Early stage partners are leaders in the design of a first of its kind full-scale testing facility in North America. The advantage of being able to include your vintage assets in the test loop. You'll also have access to new learnings now to use in your strategic hydrogen blending decisions on your system. And lastly, the financial contribution of $160,000 is very low when compared to the total capital cost to stand up the facility. It's around a 400-to-1 leverage ratio. So that concludes my presentation. Contact information for anybody who would like to reach out. Thank you very much.
Thank you, Kevin. Our last and final speaker of the day is Brendan. Please feel free to share your screen.
All right, is that up there, Tony?
Yeah.
All right, great. Thank you. All right, so hello everyone. We one more case study overview here on a blending project. So I am Brendan Shaw, process engineer at GHD, who's helped on this project, as well as multiple other ones like it over the last few years. Just to note that Dominion Energy did get acquired by Enbridge earlier this year. So I'll probably use the two names interchangeably, but let's jump in here. So quick overview again is kind of the point of this one, of this project that has been constructed. It's been operating, construction finished in 2022. So it's been operating for well over a year now. We completed, or we've done a few of these types of designs, as has been mentioned, but this is one that's been finished and is one of the more probably advanced or deluxe kind of types of it that we've done. So quick agenda here. Got a background, process overview, controls and safety, some photos about the site layout, and then mechanical details, and then some final thoughts. So this facility, Enbridge, is a training facility located in Boston Heights. It's called Hydrogen Heights. Now it's a town between Cleveland and Akron in Ohio, in the U.S. And so, as I said, so Enbridge Gas, now of Ohio, is the owner and operator, and they led the construction on the project also. GHD led the engineering and design of the project and provided a multidisciplinary staff ranging from process mechanical folks all the way to civil structural for building details and permitting, and then electrical and automation folks as well. We worked with Praxair, I think at the time, and now it's Linde, as they were the gaseous hydrogen cylinder provider, as well as a few other pieces of equipment. But the purpose of the project is really kind of as we've been talking about here today, for Enbridge to get, or Dominion at the time, now Enbridge, get familiar with hydrogen blending for natural gas between 1% and 20% hydrogen. Really just getting familiar with understanding the impacts of doing so on leaking, appliances, and just getting it so they can understand what happens in the longer term when you do this. Real with their hands-on approach. The facility itself is a large facility with several training classrooms and features. It does have 16 homes, which you'll see in a bit, and street lanterns across the site, and those are the fuel users. So how we conducted this project is kind of typical engineering, phase approach. Started with a concept, ask questions like, we're using cylinders versus an electrolyzer and solar panels for the hydrogen supply, and really just nailing down the process first. And then, along with the client, move to the feed stage or 30%, front-end engineering design to produce some preliminary drawing packages and deliverables. And once all that's all agreed and set, we'll, go into the detailed design, where we really bring all the disciplines in and really tie everything together and produce the issued for construction packages, P&IDs down to pipe layouts and foundation drawings. And finally, last stage for GHD was construction support. So one kind of noteworthy thing we did here was creating a control narrative that really assisted the Dominion programming implementers with that part of it. So the process itself is pretty high level. It's pretty simple. It's we're just really taking the existing natural gas pipeline fuel to the training facility and just adding some hydrogen into it at a controlled rate. And there is a kind of provision on the site for future on-site hydrogen production, but for this kind of phase, they just have some cylinders on site. The P&ID here is, of course, I don't know how well everyone can see it. It's probably a bit small, but of course, a bit more complicated. But it's really not too crazy. The idea is just on the bottom there is the horizontal lines on the bottom is the natural gas, and the kind of winding vertical lines is the hydrogen flow. And the control philosophy idea is just that you're controlling the hydrogen flow rate based on the natural gas flow. So if you wanted a blend of, say, 20%, then your tests would say be running at 500 SCFH. Sorry for the American or English units. And the PLC would say, okay, 500 SCFH of fuel. I have 20% hydrogen target set point. That means I need a hydrogen flow to be about 125 SCFH, and I'm just going to control that flow rate of hydrogen with the control valve and the flow meter there to just hit that rate. And as the test varies, the hydrogen will vary. I guess a few other things are we do have several safety devices, 4 different e-stops throughout the facility, 2 LEL meters, one at the building and one at the cylinders, several isolation valves to block flow upon alarm, mechanical safeties like relief valves and regulations. And then we do have 2 different gas analyzer points, one gas chromatograph after the static mixer at the blending facility, which you'll see in a minute, and one analyzer which is a kind of newer technology provided by H2 Scan, it's called, downstream of after it kind of goes back underground out to the training facility. So it's kind of next slide helps illustrate that. So this is the overview. So I don't know if you guys can see my mouse. I don't think so. The white building up in the top left after the first arrow is where the blending facility is, and the gas chromatograph building. So then it kind of comes up above ground, then goes back underground all the way to the training facility there in the green box where all the houses are, and that's where the second gas analyzer is located. Here's a couple of photos of that stub up, the existing pipeline coming up and then going back down. It's plastic underground and then carbon steel above ground. We got the 2-inch little branches off from the bypass valve there to the blending loop. Here's the couple photos of the hydrogen piping itself. So you got the cylinders there on the upper left, actually the static mixer on the bottom left. There's a hydrogen flow meter there. It's actually the smallest one that Emerson had for this application is about a 1/2-inch Coriolis. And then we got a bunch of stainless steel tubing primarily for the hydrogen piping itself. And really that's kind of the overview. I guess just some things to consider are, first is if you might want to implement something like this, what kind of control philosophy do you want to use? For us, we kind of like this flow ratio concept with analyzer verification, find it just pretty straightforward. The second is, we had pretty small flows on this project. So it kind of led us into using lab scale, GC type piping, but Dominion did have a desire to use or maintain like industrial pipeline standards. So if there was so there's a bit of an inconsistency there, like argument or whatever. And so I guess the point is if you didn't care about maintaining that pipeline standard quite as much on your site, you could probably reduce the costs a bit of the hydrogen piping at least by not trying to match everything. And then the final one is just, of course, the level of automation that you want to have on the project really impacts the cost and the duration of the project. We had a lot of duplicative instrumentation and redundancy for several operating checks. And gas chromatograph facilities and equipment are very expensive. You don't quite need that necessarily. So we've had designs with other clients that didn't really care about this as much, and it definitely reduces costs. Because final thing I'll just throw in is that, this is still generally new technology in this industry and for companies, and, it just does naturally lend itself to more revisions and iterations throughout the design process. So it's pretty much all I got. So I guess I'll send it back to you, Attorney. Thank you.
Thank you, Brendan, and thank you to all of our speakers today. I will be turning on your mics and cameras in just a second. So you should all be able to turn on your mics and cameras, and this will begin our Q&A session. So we have some in the chat already, but please feel free to just turn on your camera and ask any of our speakers a question. So our first question is from Bic Sadhu. I don't know if you're on the call. Question for Caitlin and Cole. As part of the project, did you evaluate where the hydrogen will be sourced and the hydrogen quality specifications your blending study assumptions will require?
Yeah, I can speak to that, Cole, if you want to add anything. But yeah, so it did actually start off as a commercial opportunity. And so there was a production facility that we were evaluating how much they could actually put in to their system, and that was part of our evaluation. Purity wise, that's still, I guess, like we're looking into it, and that would be dictated by the producer what they could have given us. That answers your question.
It does. Thank you.
Next question for Kevin, where will you source the hydrogen for the hydrogen to infinity project from? Will you have your own hydrogen production on site?
Hi, thanks. We will not, as of this time, we're not planning to have our own hydrogen production. That could change. The plan right now is for NCPA, who has the power plant just across the road. They're planning to have electrolytic hydrogen on site, and they will have enough production to supply our test loop. And then our blended gas might eventually be delivered to them. Right now, they're a natural gas customer for their turbine, so that in the future they might be receiving a blend of hydrogen. So getting it from NCPA is the plan.
Thank you, Kevin. And our next question is, are there lessons learned or standards developed for dedicated hydrogen pipelines that can be applied to hydrogen blending for natural gas pipelines? I'm guessing that's just to everyone.
Sure, I can chime in on that one, Turnita. I mean, there's probably 2,000 miles of 100% hydrogen pipeline worldwide. A lot of it's in the Gulf Coast. We worked on that pipeline, and generally speaking, it's stainless steel, but that's more for longevity. But depending on the size and scale of your project and the pipeline you're converting, carbon steel would be fine, depending on the pressures, the volume, et cetera, and how you manage that pipeline. So there is go-to information from decades of operation of hydrogen pipelines and oil and gas refineries, chemical plants, and natural gas pipelines to help design things depending on what your project specifics are.
Thank you, Fred. Our next question is, what purity of hydrogen are you using for injection?
For my project, I don't believe we've discussed purity of hydrogen, but it would have to be within. Actually, great question. I think that that'll be determined through the engineering design phase, the gas quality standards for the test loop. I don't expect it to be 5 nines.
And since Kevin, you're already speaking, in the PG&E pilot blending project, are the environmental attributes of the electrolytic hydrogen being tracked in the form of renewable thermal certificates?
So production of the hydrogen again belongs with Northern California Power Agency, a little bit outside our scope. But I believe that their project for the electrolysis is part of a DOE hydrogen hub through ARCHES, the Alliance for Renewable Clean Hydrogen Energy Systems. That's the hub in California, which was recently announced that they've, I believe, concluded negotiations and are funded as a hydrogen hub. So I believe that their hydrogen production, they're hoping that it'll be eligible for the hydrogen production tax credit, which means it has to meet a minimum of 4 kilograms of CO2 per kilogram hydrogen produced. There are more stringent tiers to that to get the full value of the tax credit. So I hope that helps answer the question.
Thank you. Our next question is for Brendan. Is the blending project you mentioned still up and running and using hydrogen from cylinders? How much is used per month, roughly?
It is up and running. We unfortunately haven't had, at least I personally haven't had too much follow-up from the project. I do know that one of the major things, and this is, I know, not directly answering the question or about it, but I do know one of the major follow-ups or results I heard was that they did find that there wasn't any separation of the hydrogen and natural gas as it kind of hit the training facility. As far as how much is used, it really, I gotta say, it kind of depends as far as my understanding on how many tests they're running, and what type of test. And but I think the understanding was they're not replacing those cylinders, even every week. It's more of probably maybe like you said, every 3 to 4 weeks. I think they're replacing the 12 cylinders. So hopefully that helps a little bit. But unfortunately, as a consultant, sometimes you finish a project and you hand it off and don't hear too much about it.
Great, thank you, Brendan. And then our next question is for all speakers. Do you have established recommended safety standards for transmission of hydrogen for transmission and distribution pipelines? I would assume this is PHMSA 49 SCFR 192 referenced.
I can speak for PG&E. So I don't believe that we have yet established the full slate of standards that will be applicable for hydrogen blending. I understand that the conversion of natural gas pipeline to hydrogen service, it will be kind of regulated by ASME B31.12 hydrogen pipelines, and we'll be following all of the requirements within there.
Thank you. The next question is the consideration for blending purely for decarbonizing end-use applications, i.e. residential, commercial, industrial heating and cooling, and are there other consideration for blending which can impact other industrial users that require pure natural gas for producing other products, e.g. a Dow chemical?
I can say something, but if anyone wants to jump in too, feel free. So consideration for blending purely for decarbonizing end use applications, that's definitely part of it. And maybe Cole, if you want to talk about like ACO has this great like distribution system doing the Fort Saskatchewan blending pilot and everything. Like transmission pipeline would help enable that. But it's also definitely for growing knowledge in the industry as well. You don't want to be the company that kind of like doesn't look into it if things start kicking off right away, right? And then considerations for blending, which can impact other industrial users. So an example is with our system, like we have a defined end user, and if they run their power plants off natural gas, like it's a big commercial discussion with them, because if they're not going to take it, we really wouldn't be able to blend it in our system and feed it to them, right? Like it needs to be kind of working with them. So your example is Dow Chemical. So yeah, it'd be kind of talking to them about how it affects their process, what you could do about that, et cetera, et cetera.
Yeah, that was good. And just for, and we didn't share in this presentation, but ACO is doing a lot of other work on other hydrogen initiatives and actually commissioned a few, a blending project, as well as a pure hydrogen operations center, as well as a pure hydrogen home. You can just go to our webpage, just ACO and hydrogen, and you should be able to find some more information on that. But yeah, it's definitely looking into the end user and the appliances that it's going to be impacting.
And for PG&E, our project plans to demonstrate deblending technology for end users who require either pure methane or pure hydrogen. That technology is developing, and we hope that that can be one way that we could blend into the system and still provide either pure fuel to any customer who requests it.
We have somebody with their hand up.
Hi, just one more question. Is there any consideration for converting a large transition pipeline into 100% hydrogen? Is any company, is any one of your companies doing that, looking at converting a transmission pipeline, an existing transmission pipeline for 100% hydrogen?
That's the project that me and Caitlin are talking about. Looking at converting it to pure hydrogen, but also assessing if it can't be converted to pure hydrogen due to implications possibly on the end user. Looking at what kind of blends and stuff we can do, but currently looking at converting to pure hydrogen.
Okay. But I'm thinking of like a TC, for example, that's transmitting hydrogen or natural gas for a customer. Again, my understanding is the ACO project is for an end user for heating applications, but to convert to transport 100% hydrogen. That's a project that you're working on. Cool.
Yeah, that the high pressure transmission that we're looking at converting would be to pure hydrogen. We also have other like blended projects and stuff like that, but the project me and Caitlin discussed would be a transmission converted to pure hydrogen.
All right, sounds good. Thank you.
And we are right at the hour. So thank you so much to all our speakers today for your wonderful presentations. And thank you to everybody for attending. Right after this, I will be sending all of the presenters slide decks and the recording of this. So watch out for that. And yeah, thank you everyone again and have a great, wonderful rest of the week.
Thank you.
Thank you, everyone.
Good
Thanks so
deal.
much. Bye.
Thanks.
Thank you, everyone.